last time we finished book 9, finished Euclid's number theory, up to book 9. These are books 7 through 9 are the number theory books. The big boss there was, anybody remember? Not what number it was, but what the content was. I don't remember the number.
1 + 2 + 4 + 8 + 2, etc., etc.
Yes. Yes. The construction of perfect numbers given what are now called Mersenne primes. Okay. That was that's where we ended. For the next book. For the next book, we get into book 10. Okay, so book 10. Book 10, let's have a look at it. Here's book 10. Definition 1. Those magnitudes that are said to be commensurable with one another are those which are measured by the same measure. Just. Yes. So on Tuesday, we'll go over everything that we, it's going to be a quick little thing. We just want to get into this thing where we have a homework, then we have a quiz on it, then we have, easy. Easy, but keeping like a light job, right? Okay. Those magnitudes that are commensurate are measured by the same measure. So that's, we understand what that means. He's referring yet again to the Pythagorean notion of commensurability and issues therein, and the Euclidean algorithm for finding GCD, if indeed things are measured by the same unit. Right? Everybody understands what I'm saying, and otherwise they're called incommensurable. We're not going to go over this book. This is actually my least favorite book. The stuff that he's doing, he's really struggling with the fact that he doesn't have modern notation. It's very long. People say it's among his most ingenious books because of the kinds of things that he has to prove. Like this, none of this stuff excites me. The big boss is from the medial straight line. There arise irrational straight lines, infinite in number. None of them is the same as any preceding. He's like constructing many irrationalities. We're going to move past book 10. So, but what is in book 10? Incommensurability. Okay, so he's studying incommensurability. Irrational, what we would today think of as irrationality, irrational ratios, etc. Okay, so again, in that Pythagorean tradition, this book is addressing some very old things. Books, we're almost there. That's book 10. There's only 13. So 11 through 13, books 11 through 13 deal with solids. So everything we've been doing so far has been about plane objects. We finally get to some solid geometry. And let's just have a look at that. So here's book 11. The first definition is a solid. It's something that has breadth and length and depth. Okay, 3 dimensions. Again, you should not say such things because what does depth mean? What does breadth mean? And you get this infinite recursion. The face of a solid is a surface. Okay, so the face of a, by face, I mean a 2-dimensional object. Solids are made up of 2-dimensional faces. A straight line is at right angles to a plane when it makes a right angle with any line in that plane. Okay, so this is like what we would call a normal line to a plane. Inclination, so we're not going to go through again these things in any detail. Parallel planes are planes which do not meet in space. He doesn't have to say the word in space because it's obvious what he means. A solid angle, when two planes cross each other, how do you measure what's called the dihedral angle between those? A pyramid, you have some shape and a point on top, and just take the cone up to that point. You know what I mean? Definition 12. Let's just, I'll write down a couple of these things. Definition 12. Definition 12. Pyramid. A pyramid is you have any shape you want over here, like that, and then you have an apex, and then you just, that's a solid that we'll want to think about, right? Pyramid, the great pyramids in Giza. Definition 13 is a prism. So what's a prism? Anybody know what a prism is mathematically? Not so different from what it is in crystallography or something. You take a shape, I'll take like a, I don't know what this is going to come out to be, a pentagon, and you take the same shape and just slide it up, and then you connect it vertically, okay? So that's what a prism is. Okay, does that make sense? So a prism is a solid figure contained by two planes, which those opposite sides are equal and similar and parallel, and the rest are parallelograms. Okay. So you have two weird faces, and then you have these parallelogram faces. All right, we're not going to go, again, we're not going to go through any of this in detail. We have the axis of a sphere, we have the center of a sphere, we have the diameter of a sphere, axis of a cone, the base of a cone. He's explaining what all these things are. Let's not go through this in any detail. There are just a few things that I want to highlight. For example, book 11, proposition 21. This will be important in what I want to say. 21 says a solid angle is contained by plane angles whose sum is less than 4 right angles. So let's isolate this one. This will be needed. This is book 11, proposition 21, I think we just said. A solid angle. What's a solid angle? You have a bunch of things coming together to a corner, like a vertex. Solid angle, meaning total dihedral angles around a corner, or what we would call vertex. I'm trying to throw in some mathematical nomenclature so that you're exposed to it. I'm not quizzing you on vocabulary right now. A solid angle is always less than 4 right angles. Okay, so let's think about that. I have some toys here. Poor children never get to play with their things because I keep stealing them. Okay, so a solid angle is like a corner. And what's this angle? Can you see? What's that angle? These are equilateral triangles. Yeah, so that's 60 degrees. And what's this angle? 60. And if I stick a pentagon right here, I'll actually do it. Can I do this in real time? I think so. I need smaller fingers. There we go. So there's a solid angle. I've got 60 degrees there. I've got 60 degrees there. I've got, how much is a pentagon? Anybody know how many angles there are in a pentagon? Let's work that out for 1 second. You know how to work this out? That's a good guess. On the inside of a pentagon, I heard 2 things, sorry. On the inside of a pentagon, it is 360 divided by 5. That's actually a good way one way of working it out. So if the inside is 360 divided by 5, that makes the inside. How do you divide by 5? You double and then shift the decimal point, right? 5 is multiplying by 5 is multiplying by 10 and dividing by 2. 72. Right? 72 times 5 is, so if that's 72, then how much is each of these? Well, what's the sum of those two? 108. So actually, we don't need to know anymore because what I really want is that angle, and that angle will be the sum. So that angle is 108. Okay, so this angle is 108 degrees. So what this 1121 is saying is that the sum of, I guess I shouldn't call them dihedral angles are the angles at which 2 planes meet. Like if these two, imagine the plane between this pentagon and this triangle, that's the dihedral angle between them. This is the plane angle, the angle in the plane. That's a better way of saying this. Where's my little total plane angles around a corner a vertex is less than 4 right angles. So let's just look at that for 1 second. Here, I'll stick another triangle in here. How much is 4 right angles? 360. Okay, so I've stuck together 3 equilateral triangles and 1 pentagon. So around this corner, I have how many angles? 60, another 60, another 60, 180, and 102, 108. Well, 108 is less than 180. So whatever is around this corner is not going to be more than 360 degrees. Why? What if it was 360 degrees? I mean, yeah, then that corner around this vertex would be 360 degrees, which means we've used up all of the angles around it. So it's actually not a corner. It's part of a face. Right? Does that make sense? So it has to be strictly less than 360 degrees around any corner of a solid. Alice. How do I got 180 in where? In the 108, yeah. So the inner this 72, oops, the 72 is 360 over 5. Because there's 5 of these triangles from the inside. And so if this inner angle is 72, then the 2 base angles of this isosceles triangle will be 180 minus 72, but divided in half. And then if I want the full angle of the pentagon, it's double the little angle. So don't bother dividing it in half and doubling it, just leave it as 108. Does that make sense? Okay, great. So I want to isolate that, as you'll see in a second. We're going to need that. Who's the big boss in this book? We go all the way down to proposition 39. So big boss, let's write this down. Big boss of book 10. Big boss is 11.39, which says, okay, if you have 2 prisms with equal height, one of them has a parallelogram base, AEFC. The other one has a triangle base. Don't bother writing this down. This isn't important. I just want you to sort of see the kinds of things that he's doing. One of them has a parallelogram base. The other one has a triangle base. And I assume that the parallelogram is double the triangle. That would be the situation if they were between 2 parallels, but I can't put them on the same parallel because I don't have enough room to put the 2 prisms together. So why are these both prisms? Remember what a prism is? You have something on top, something on bottom, and then it's just rectilinear in between, parallelograms in between. So what he's saying is this is a triangular prism. Like, I'm going to try to draw it here. If I have a triangle and another triangle, and then I make a prism between them. Okay, and I'm worried about the base. The base is this bottom side. Or I have just a regular looking prism, which is a triangle and another triangle, and then some height. And then this is the other base. And then if this height is the same as that height, and this bottom is equal to twice that bottom, then the pyramids have the same volume. So pyramids, these different, they're not pyramids, they're prisms. Prisms have same volume. All right, this is just a warm-up. This is like some very simple stuff with rectilinear shapes. Okay. If the parallelogram is double the triangle, then the prisms are equal. Okay, that makes sense? Not a big deal. We're moving right on from book 11 to book 12. In book 12, he does some very interesting things. For example, here's proposition, look at proposition 2. So this is book 12, proposition 2. Book 12, proposition 2 is that circles, let me let you read it. Cindy her quiz. Circles are to one another as squares on their diameter. Does that sound familiar? Circles are to one another as squares on their diameter. So the ratio of the area of a circle to a square on its diameter is the same as some other circle relative to the square on its diameter. Did we ever need that? When? Emilia? Okay. Yes. Quadrature of, Lori? The loon. Yeah, Hippocrates needed this for the quadrature of the loon. Here it is appearing now with, we don't, I mentioned that it's not clear if Hippocrates actually knew how to prove this properly, but here it is in book 12, proposition 2. Yes. Yeah, that little. Yeah, the way we prove the quadrature, the reason we had quadrature of that was that we knew when we doubled, when we increased the base by a factor of square root of 2, it turns out, it made the area double. Yeah. So it's like the areas of circles, hopefully this doesn't look like a sphere, this is just meant to be a diameter. So areas of circles is quadratic, area is some constant times the diameter squared. Okay, that's what this book. Now, why does he put this here? This has nothing to do with solids. He could have proved this long ago. He's not using any new technology here. Who's the big boss? Let's look at the big boss. Proposition 18. Spheres are to one another in triplicate ratio of their respective diameters. Okay, so the big boss in book 12, proposition 18, is that spheres are onto one another in triplicate ratio. So I'm going to try to draw a cube whose side length is the diameter of the sphere, is the same as the ratio of some other sphere to a cube on its diameter. That's how he's thinking about this. Okay, we would say the volume of a sphere is equal to some constant, different constant, C prime, times the diameter cubed. Does that make sense? So again, this is about the structure of the elements. This is like a beautiful symphony where a theme, he's going to suppress this fact about circles, even though he could have proved it long ago, because he wants to put it where it, for him, logically belongs, which is next to the sphere, next to where he does this for the sphere. We're going to come back to these two also. But that's the big boss in book 12. Finally, we're in book 13, and the real big boss for book 13 is this remark. So proposition 17, let's go to book 13. Book 13, proposition 17 constructs the dodecahedron. We're going to talk about what that is, dodecahedron. And then the remark after proposition 18, and what I call the big boss is this remark, unnamed, unnumbered remark that he's constructed all the Platonic solids, has constructed all the Platonic solids. Okay, so I have to tell you what the dodecahedron is. I have to tell you what the Platonic solids are, what Plato has to do with this. So let's go. Okay, so Platonic solids, let me give you a definition. Remember, we talked about regular n-gons. What's a regular n-gon? Regular polygon. What does that mean? What does the word regular? Say it again. We were worried about for which n can a regular n-gon be constructed, but we can still define an n-gon for any n. Alicia? Say it again. In 2D. Amelia? Yes. So recall definition, a polygon, just we're in 2D, polygon in 2D is regular if all sides are the same and all angles are the same. Right? So that's why it's got such a nice shape to it. We started with the regular 3-gon this entire journey. We're at the end of the journey. We're done with the elements nearly. We started with the regular 3-gon. Started book 1, proposition 1 with regular 3-gon, also known as an equilateral triangle, i.e. equilateral triangle. Okay. What is the analogous object in 1 dimension higher? What's a regular solid? It's a definition, a regular solid, also AKA Platonic solid, is one where is a solid having all sides the same, all angles the same. That could mean both dihedral angles and like all corners the same, all corners the same, and all faces the same. Basically, anything you can ask for the solid, I want it to be perfectly symmetric. Okay, so what can you do? So let's try to find some of these. Try to construct some of these. You could take equilateral triangles, right? That's the smallest. The faces themselves have to have all angles and sides the same. So the faces have to be regular n-gons. Okay, so faces must be regular n-gons. 3-gons, triangles, 4-gons, squares, 5-gons, regular pentagons, hexagons, and so on. Okay, whatever the faces are. One of the things that he proves is at every corner, there have to be at least 3 shapes. You can't have 2 shapes. 2 shapes can't meet at a corner. That doesn't leave any room. Okay, and must have at least 3 of these n-gons meeting at each corner. Okay, so could you have try 3? So you can't have 2, so let's try 3 equilateral triangles, three regular 3-gons meeting at each corner. And down. Get them later. Okay, so here, let me try to use color so you can see. So here, toys are great. Who doesn't like toys? Here is what it looks like when 3 equilateral triangles meet at one corner. And the question is, can I keep that pattern going and fill up a solid? So I'll grab another equilateral triangle, and lo and behold, I can fit 4 equilateral triangles together where every single corner looks the same as any other, any side is the same, any angle is the same, any dihedral angle is the same. That's just this perfect little shape. Anybody know what this shape is called? Pyramid, yes, yeah, it is a pyramid. How many? You're absolutely right. It also has a special name. Pyramids are more general, so like rectangles are more general than squares. A square is a rectangle, but there's a even fancier name for it. Just like we say regular, equilateral triangle or square, it starts with a T. How many faces does it have? It's got the 3 sides and 1 base. So 4. Anybody play a game when you were little with like 4 little squares that that are falling down? Tetris because of 4, tetrahedron. This is a tetrahedron, okay? So this is a try 3 triangles, makes a pyramid, makes a perfect pyramid called a tetrahedron. Hedron, as opposed to gon, is a solid as opposed to a flat shape. Okay, tetra is 4. Tetris. Tetra is 4. Okay, fine. So we can do this with 3 triangles meeting at a corner. Could we have 4 triangles meeting at a corner? I might use some assistance up here if somebody has fingernails and can. Oh, now that I've closed this up, there's no way to open it in small hands. There we go. Okay. Could we have, instead of 3 triangles all meeting at a corner, could we have 4 triangles coming together at a corner? Why not? Let's see what that will do. Okay, here's 4 triangles meeting at a corner, makes a little hat. It's still got some wiggle room. So I have to continue this pattern everywhere. So if there were 4 triangles meeting at this corner, there have to be 4 triangles meeting at this corner. I've got 2 so far. I've got to add 2 more triangles. So let's add, everybody see what I'm doing? Let's add 2 more triangles to this corner. And we're starting to fill out the shape. We still have a little bit of wiggle room, a little Pac-Man. Now I have this side, which has 3 triangles. I need another triangle at this corner. Here it is. Make sure you can see. Yeah. Okay, and I'm not going to close it up because then it'll be too hard to open it, but you can see that there's just space for 1 more triangle right there. Okay, so this is a shape that has 4 triangles at every single corner. Every face is a regular 3-gon equilateral triangle. And how many of them are there total? How many on top? 4, because that's at this corner. How many on bottom? 4. 4 plus 4 is, so what do you think this is called? Octahedron. Okay, this is the octahedron. So try 4 triangles, 4 triangles around every corner forms an octahedron. Okay, let's draw little pictures of these. Nope. We're just starting out with triangles and seeing how far we can get. Josie? So pyramid can mean just any shape whatsoever on bottom. Just like make some kind of polygon, whatever. I'm gonna even make a really weird, and then 1 apex, and then connect all of these. So you have some shape in a single plane, and then a single apex out of it. And so a pyramid would be this. Okay, so I want a regular pyramid, which means it's the same everywhere all around. The base is the same as any of the sides. That's a perfect, yeah, that's a perfect regular pyramid, which has the name tetrahedron. Okay, and then if we have 4 triangles around every corner, so here's a corner that has 4 triangles around it. Hopefully you can see there's this like square. There's a square down the middle. In fact, if you take a square pyramid, a perfect square pyramid, and just glue another square pyramid to the bottom, what you'll get is the octahedron. Okay. By the way, how many angles around each corner are there? Sum of the angles. This, in a tetrahedron, we had 60 degrees, another 60 degrees, another 60 degrees. 3 times 60. 180. 180 degrees. 180 is less than 360. Okay. How about in an octahedron? How many angles are there around every corner? I've got 60. How many plane angles? 60, 60, 60, 60. There's 4 equilateral triangles. Each equilateral triangle has 60. Sum of the angles, sum of the plane angles is equal to, 4 times 60, 240. 240 is still less than 360. So far, so good? Around a single corner, but all the corners are the same. So you look at a single corner, you say, I've got 4 60s, 4 60s adds up to 240. That's less than 360, and that's why this, that makes sense. So far, so good? Okay, how about 5 triangles? Try 5 triangles around each corner, vertex. So now, if I really took the time to do this, it would take a good 5 minutes. So we're not going to do that. In fact, maybe I'll ask for a volunteer to help. So this is what 5 triangles looks like. And now I've got this corner that only has 2 triangles, so I have to add 3 more. So here's 2 more. Does anybody like playing with, whoops, I can't close it up. If I close this up, I've got 4 triangles around this corner, but 5 triangles around that corner. That wouldn't be regular. Okay, so I've got to put 1 more triangle in here. And now I at least have 2 vertices. This vertex has 5 triangles around it. This vertex has 5 triangles around it. Anybody like playing with toys? Okay, Jillian. Nargis, you want to come help Jillian? So here's a whole bunch of triangles. I'm gonna keep a couple of triangles for myself. And here's some more triangles. And I'll give you more triangles in just a second. Got a man down here. Ready? Okay. So while Jillian is seeing what will happen if we try to put 5 triangles around every corner, let's see what happens if we do 6. So I'll leave a little bit of room. Try 6 triangles at each corner. Amelia already sees a problem. That's exactly right. So here's 4 triangles, and here's 2 more. And if I make 4 triangles, so now we have 6 triangles around this corner. What's the problem? As Amelia just said, it's flat. I don't have any curvature left. There's nothing I can do with this. I can continue making more and more triangles, and it will just go on forever and fill out a plane. It's the tiling of the plane by equilateral triangles or by hexagons, if you like. Okay, so 6 times 360, 6 times 60, right? That's each triangle is 60 degrees, and if there's 6 of them around, 6 times 60 is 360, which is not strictly less than 360. And so corner does not have is not solid. Is not solid. So that corner is not solid. And continuing, let me write this in English. Continuing to place 6 triangles at each vertex, there's nothing wrong with it. It would tile the plane by equilateral triangles, or what's the same, hexagons. Okay, hopefully that makes sense. Everybody see that? It would just continue forever in this way. Yes. Oh, I'm so glad you asked. I'm so glad that you asked. What if you added 1 more? So here we go. Let's add 1 more. What if we had 7 triangles at each corner? Love that question. What kind of geometry do we get now? So when we had 3, 4, or 5, we got something that closed up and became spherical, right? You can think of these. You can think of the tetrahedron as being some crude approximation to a sphere. Same with an octahedron. We're about to find out what happens with that shape. You ready for some more triangles? Yeah. Ready? 1 more. Okay. Oops. Here's what happens if you start adding too many triangles. What is this? You guys are so good. That's exactly right. If you take a whole mess load of these triangles and at every corner you put 7, and at this corner I'm going to put 5 more, and at that corner you get this scrunchy, crazy thing. By the way, it's going to be flexible, unlike all of those. That's something called Teichmuller geometry. So it's not what Euclid was thinking about, but you guys are so good. So 6 triangles will 6 triangles will make flat space, or the flat plane, which has 0 curvature. We talked about curvature at some point for a second, or maybe that was just after class. I'll tell you about curvature in 1 second, and we'll move on. But 7, if we put 7 triangles around every corner, then this will have negative curvature. This will approximate negative curvature. Negative curvature approximate the hyperbolic, negative curvature hyperbolic space. Hyperbolic. Okay. I added a link in the course page to hyperbolic crochet website where you can see how people are making, with cloth approximations to, or with string, I guess, approximations to this kind of shape. How far did you get? You need some more triangles? Ready? Okay, so Jillian's almost done. So while Jillian works on that, so you see what will happen. We can put any number of triangles around. It's just that only when we have 3, 4, or 5 do we get something that at least has the chance of closing up. We'll see what happens with 5. If we move from triangles to squares, what can we do with squares? How about this in English? How about 3 squares? We need at least 3. The shape has to be the same. I didn't bother bringing squares because I think you can imagine what happens if you put 3 squares at a corner. What's that called? If you continue putting 3 squares at every corner, all the way around. So here's 1 square, here's a 2nd square, poorly drawn, and here's a 3rd square. Then I have to put, at this corner, I have to put a 3rd square. And then at this corner, I have to put a 3rd square. And now every corner has 3 squares. That's a cube. Okay, that's a cube. Or a regular sexahedron. Nobody calls it a sexahedron. Hexahedron. Okay. Hexahedron. All right. How about 4 squares? What's the total angle when I put 4 squares together? 360. 4 times 90 is 360. So we'll tile the plane. Okay, tiles the plane. And of course, I can't put 5 squares without, 5 squares will take me into hyperbolic. Okay, so that's it for squares. All right, so we've got this guy, the cube. How are we almost done? Okay, good. Oh, perfect. Here, can I have it back? All right, so I'll take this one triangle off so we can see the rest of the shape. So this is really cool. Great job. So at every corner, there are 5 triangles all the way around, and it looks exactly the same. And the question is, so 5 times 60 is, let's scroll up a little. Where are we? Right there. 5 times 60. $300, which is less than 360. Now, it's not obvious when you start doing this that you'll be able to finish. Right? It's not clear that just because you can make one corner work and then you can make the next corner work and you can make the next corner work, that when you go all the way around, you'll actually close up and make a perfect shape like this. Okay. Let's figure out how many triangles this has. There's obviously 5 here. It looks like there's also 5 on bottom. These 5 connect to like 5 going down here. Let me try to draw it here. So we have 5 triangles on top. 1, 2, 3, 4, 5. Okay, they make this pentagonal cross section. This little pentagon here. Okay. Each of those comes down to 5 more triangles. Those 5 connect to 5 other triangles, making another pentagon. And then that pentagon has 5 more triangles coming down to the bottom. Okay, so there's 5 on top. There's these 5 drooping down from the 5 on top. There's 5 more coming up and interspersing these 5. And then there's the 5 on the bottom. Amelia. Yes, actually, I'm told. I don't actually play Dungeons and Dragons, but I'm told that I've seen that they use like 60-sided die, and there's other ways of making fair die. This is a very interesting mathematical problem, actually. But yes, the fact that we mostly use the cube, the 6-sided die, there's no reason for that. We could just as well use a 4-sided die, tetrahedron, or an 8-sided die, the octahedron, or the how many sides? 20. There's 4 layers of 5. 5 on top, 5 facing down, 5 facing up, and 5 on bottom. Of course, there is no top and bottom. Every corner looks just like every other. Okay, so there's 20 sides. Anybody know what 20-sided shapes are going to be called? Icosahedron. Very good. Icosahedron. Okay, so our basic shapes are tetrahedron, octahedron, icosahedron. Now we've got this hexahedron called a cube. We can't do anything more with 4 squares. What can we do with pentagons? Right? 4 squares will tile the plane. 3 squares will make a cube. 3 times 90 is 270. How about a pentagon? What's the angle in a pentagon? Anybody remember? We just did it. 108. 108. And what's 3 times 108? What is it? 324, which is less than 360. So there's a chance. 3 pentagons can meet. Put pen down. I had it right the first time. 3 pentagons can meet at a corner and begin a shape. The question is, will it continue a shape? So Jillian, you got it last time. Nargis, you wanted it, right? You ready? Catch. Here's some more coming your way. Couple more. Watch your eyes. Okay. And just a couple more. Oh, my bad throw. Ready? One more. All right. Let's see what you can do with that. So we'll come back to what happens with 3 pentagons. So we're going to try 3 pentagons at each corner. While we work on that, let's see what else we could do. Could we do 4 pentagons? Why not? Too much, right? 4 pentagons is too much. 4 pentagons, 4 times 108 is greater than 360. No good. No good if you're trying to make a spherical object. Of course, it's plenty good if you want to make a hyperbolic object. Fine, so we're done with pentagons. How about 3 hexagons? 3 hexagons. What will happen if you try to put 3 what's the side in a hexagon? What's the angle rather? That's not a hexagon. That's a hexagon. 120. 120 because it's 6 equilateral triangles, right? So you have 60 and 60. There's a equilateral triangle in the middle here. This is 60, that's 60. That whole angle is 120. 3 times 120 is less than 360. No, it isn't. It's equal to 360. So what will happen if you start putting 3 hexagons together? It's going to be flat. You're going to tile the plane. Okay, so 3 hexagons. Here's a second hexagon, and here's a third hexagon. And they will perfectly go around that corner and tile a flat plane. So this tiles the plane. So we won't be able to make anything out of 3 anything spherical out of 3 hexagons. 4 hexagons, no chance. We already can't do it with 3. No more with hexagons. So no options, in fact, no options with hexagons. How about septagons? It's already too big. You can't even put 3 of them together in the plane. Okay, already 3 together are too big, are too much. So it's clear nothing else is possible. Anything larger than that, you can't even fit 3 of them around a vertex and make less than 360 degrees. So nothing else is possible. Our only options only options are, let's see, I have to start a new page. Only options are three triangles, three equilateral triangles meeting in a corner. That does make a shape. It makes the tetrahedron. Or four triangles all coming together. That makes the octahedron. Or five triangles coming together. Icosahedron. Six triangles is too much. How about squares? Three squares. The cube. Four squares is too much. How about three pentagons? Well, we don't know yet. How close are we? Oh, you got it. Yes, just in time. You can pass it up.
Yeah, it's my masterpiece.
Great job. Yeah, no, it's all right. Yeah, sure. Okay, I'll take one side off so that we can look inside if we want to. All right. Every corner is made up of three pentagons. And it does close up. There's a last pentagon that we can fit in here, and the whole thing comes together. How many pentagons are here? There's one on top, one on bottom. Because it's a pentagon, there's 5 around this one and 5 around that one. 12. 5 and 5, 1 and 1, exactly. So this is the dodecahedron. Dodeca means 12. Okay, so let's go back here. Try 3 pentagons at each corner. Makes a 12-sided shape. Again, the schematic is a pentagon on top, a pentagon on bottom. Well, let's draw pentagons around. I can't draw this. It's too hard. Okay, I'll try. Like that. And then something like that. And then there's it's too hard to draw. Okay, so it's some funny shape with pentagons around, and then another round of pentagons below that in order to fit in a pentagon over there. Okay, hopefully okay, here. This is what it looks like. That's why I brought these in, right? So I don't have to draw these things. And again, 3 pentagons works because the 3 times 108 is less than 360. And 12 is called a dodecahedron. Dodeca equals 12. Regular 12-sided shape. These have interesting properties. I'll just illustrate a couple of these. Where's my octahedron? Oh, of course, I would have to take this apart to show you the octahedron. Okay, there are, this is the icosahedron. Okay, so it's 3 triangles at each corner. 3 triangles meet at the corners. 20 triangles total. 20 triangles total. And how many corners are there? We know how many sides, but how many corners? There's 1 corner on top. There's 1 corner on the bottom. Then there's 5 as you go around this inner pentagon, and 5 as you go around that inner pentagon. So number of corners, 12 corners, 12 vertices. Okay. How about this? What's the other one that I have up? How about the dodecahedron? We said this one is 3 pentagons at each corner. Per corner. Makes how many pentagons total? Dodeca, 12 pentagons. 12 pentagons total. Total. How many corners? Let's count the corners. Let's see. We have a pentagon on top. That has 5 corners. We've got a pentagon on bottom. That makes 5 corners. And we've got 2 kinds of corners. There's the high corners and the low corners. And there's 5 high corners going around. And there's 5 low corners going around. So if we look at corners just graded by the height, there's 5 corners all the way up here. There's another 5 at this height, another 5 at that height, another 5 at that height. Everybody see that? What did you say? 20. 20 corners. They're very, very closely related. What's the relationship? They are cousins. They're called duals. I like cousins better, but unfortunately, for whatever reasons, mathematicians did not decide to call these cousins. They decided to call them duals. These are dual polyhedra. The dual happens when you replace, when you think about, instead of corners, turn corners into faces. If I think of this corner as a face, and I think of this corner as a face, and that corner as a face, the way that the corners, the role of corners and faces interchange is exactly the thing that takes you from this shape to this shape. These are cousins. Josie. I'm sorry, thank you very much. This is not 3 triangles, this is 5 triangles. Thank you. These are dual polyhedra. You replace corners with faces. Like if you think about like trying to shrink this one down, this pentagon down to a corner, and shrink all of the pentagons down to little corners, what you would be left with is a bunch of triangles, because these 3 would shrink and you'd have triangles inside of them. These things are hard to visualize. I just want to throw that out there. By the way, in a cube, let's go back up here. In a cube, there are how many faces of a cube? 6-sided die, right? 6 faces. So a cube, let me put it over here. Cube has 6 faces. And how many corners? 4 on top, 4 on bottom, 8 corners. How about a, what was this called when we had this octahedral shape? How many faces? Octa, 8. How about corners? 1 on top, 1 on bottom, and a square of corners in between. 6. So what? They're dual. The octahedron and the cube are dual. Okay, the octahedron and the cube are also dual. And this one you can really draw. Here, I'll draw it on the cube. I'm going to turn, let me get a color. I'm going to turn this face, the top face, into just a corner. I'm going to turn the bottom face into a corner. I'm going to turn each of these faces into, like I'm drawing the centers of the faces. And I'll connect an edge between any 2 faces that are tangent. So the left side and the top side share an edge. So I'm going to connect the left side and the top side. And the back and the top also share an edge. I mean, yeah, they share an edge. The right side and the top share an edge. And the front and the top share an edge. And the same thing happens with the bottom. The bottoms in all of these share edges. And all the way around, we share edges. Does everybody see the duality between the cube and the octahedron? So that's cool. These guys have cousins. The dodecahedron has a cousin, icosahedron. The cube has a cousin, which is the octahedron. Poor tetrahedron's all alone. Who's his friend? He plays with himself. He's his own friend. Poor guy. That doesn't sound right. The I'll just show you what's going on with the tetrahedron. Here's the tetrahedron. He has nobody to hang out with. Oh, this is really badly drawn. Let me put this more over here. There we go. Okay. So there's your tetrahedron. Okay, you see that? Four shapes. And now let's draw. I'm going to draw the centers of all the faces. This is the front face. This is the bottom face. This is the side face, and that's the back face. And everybody's connected to everybody. So hopefully you see the tetrahedron is dual to itself. Okay, so it's self-dual. Tetrahedron is self-dual. Okay, why are these called Platonic solids? Let's go back for a second. So, so what's the theorem? We just classified the theorem, these 5 solids. Let's write this in English. Theorem, these 5 solids are the only regular solids. And they're called the Platonic after Plato. And that theorem is this remark. No other figure besides the said 5 figures can be constructed by equilateral and equally angular figures equal to one another. Let's look at the remark. For a solid angle cannot be constructed with 2 triangles, or indeed planes. You need more than 2. With 3 triangles, the angle of the pyramid is constructed, pyramid meaning tetrahedron. 4, the angle of the octahedron. And with 5, the angle of the icosahedron. He's talking about angles, but that's because he's sort of trying to project everything and understand it from angles. But a solid angle cannot be formed with 6 equilateral and equiangular triangles, for the angle of the equilateral triangle being 2/3 of a right angle. 60 degrees is 2/3 of 90 degrees. The 6 would equal 4 right angles, which is impossible. Okay. For the same reason, neither can a solid be constructed with more than 6 plane angles. So you can't have more than 6 of anything, because the triangle is the smallest thing you could try to fit. Okay, so you can't have 6 of anything. By 3 squares, you get the cube, but 4 is impossible because they would again be 4 right angles. 3 equilateral and equiangular pentagons, the angle of the dodecahedron is contained. Okay, so that's this thing. But 4 is impossible to have a solid angle because the angle being of the pentagon, the 4 angles would be greater than 4 right angles. Neither again will any solid be contained by polygonal figures other than the ones we've described by reason of absurdity. That's the classification of regular solids. So for n-gons, you can have an n-gon whatever you want. For n-hedron, there's 5 and that's it. And they're the only ones. Okay, let's just do a little bit of history here. So again, just to reorient ourselves, if this is the Pythagoreans, and then what 450-ish is Hippocrates. And then we talked about around, I'll put it over here, 350 was Alexander the Great, who sets up the city of Alexandria, which is where in the year 300 we get Euclid. By the way, let's put Eudoxus on here as well. Eudoxus is around 400, just because of the big impact he had on the books we discussed, Joseph. So meaning, where does he say? So it's part of what he says in the definition. I mean, he doesn't explicitly call it a Platonic solid, but first so proposition 13 is the construction of the tetrahedron to construct a pyramid, which is what Layla called the tetrahedron. So you're following Euclid. Yeah, good. Then the octahedron, and comprehend it in a sphere to construct a cube, to construct the icosahedron, and finally the dodecahedron. So he constructs them one by one. Then he shows that they're the only ones possible, and that's the remark. And this is the very end. This is the very, very end. We're done with the elements. Yep. This is the finale right here. He constructs this thing, says there's no more. The end. Right. Okay. So there are 3 other people that we could throw on here. One is, they're not mathematicians, but they're still important people for you to know. So Socrates teaches Plato. Plato goes to Athens and creates the academy. Euclid is studying in Alexandria. Euclid of Alexandria. This is why I put Alexander the Great here. So this is North Egypt, North Africa in Egypt. Plato's Academy is in Athens. This is in Athens. Plato teaches a guy named Aristotle, and Aristotle teaches Alexander the Great. Okay, so Alexander the Great has a great respect. Now, Plato is not himself a mathematician. Okay, let's not. Lots of societies who asked these kinds of questions came to these conclusions. Right. This is one of the things that if you were sending a probe out into space, you would want aliens to know that we've understood something. You just draw the 5 Platonic solids, and they go, "Oh, these guys understand something." I mean, and they made a spaceship, so they understand something. But like, there's some deep mathematics there. So Plato knows that there are these 5 Platonic solids. He also knows that there are the elements that make up the universe. People were thinking about like atoms. They had no idea what atoms. They did not understand the modern version of atoms. They're like, you take something, you break it up into something smaller, you break that up into something smaller, and at some point you get to the end. And that end is what we'll call an atom, the thing that can't be broken up, which, by the way, ties in beautifully to number theory. Because any number, you break up and break up and break up, and then you get a prime. And the primes are the atoms of the multiplicative numbers universe. So Plato's, what people conceived of, like what are the objects that we interact with all the time? We have Earth, right? The ground. Everyone understands that there's something called, they thought of the ground as an atom, like a little atom of Earth. They thought of air, a little atom of air. We obviously can feel that we're breathing something. There's something around you. You have wind, like there's something there. There's water. Everybody needs to drink. There's water, and there's fire. So Plato said the earth is very stable. So he considered the earth as the cube. That's like, you can just plot a whole bunch of cubes and it'll make up the earth, and that's great. Water rolls. Water is so like flowy. What's the flowiest thing? The sphere is the flowiest thing. So what does he consider water? The dodecahedron is the closest to a sphere, the rolliest. I'm sorry, that's not right. The icosahedron has the most number of faces and is the rolliest. So the icosahedron is water. What's the like sharpest thing, the thing that'll hurt you if you touch it? The tetrahedron. So he's going to make that fire. Tetrahedron is fire. How about air? It's sort of dual to earth somehow. He makes that the octahedron. And then he says, okay, job well done. Wait, there's one more. And where does it fit? So he says, oh yeah, well that dodecahedron, I mean, the gods just used that to make the heavens or something. He just sort of, audibles it. I don't know what to do with this thing. And then there's one more here, and I don't know what happens to it. Aristotle says, oh, that's ether. Aristotle proposes, so Aristotle says maybe this is something like ether. Of course, not in the modern understanding of ether as a medium through which light was supposed to move, even though now we know light moves through a vacuum. But that's kind of what's going on there. Okay, that's the elements. Yay. That was a big chunk of what we wanted to accomplish. Now we get to move on. So the next big name, again, these are all very rough. You can read the exact dates. I'm not asking you to know the exact dates. And to me, they're not important. What's important is the sort of chronology of how these things happen, what ideas people are exposing themselves to and the world to. The next major name that we're going to study is the greatest of the ancients. A guy named, who is it? Alexander the Great. No, he's great at conquering stuff. He's good at killing people and then setting up some infrastructure afterwards. Good guess. You're Emilia. It's the one that starts with A, but it's not Amelia. Archimedes, the great Archimedes. Okay, so that's the great Archimedes. Anybody know where Archimedes is living? Modern, he's living in modern Sicily in a city called, it's in upstate New York, Syracuse. Yes, so Archimedes of Syracuse. This is in Sicily. So Archimedes, he has a long-standing collaboration, not collaboration, but he sends a lot of letters back and forth with a guy we will talk about more, named Eratosthenes. Let me not even write down Eratosthenes. Eratosthenes is the head librarian of the Library of Alexandria, which has now been around for a century and contains, it's like the Library of Congress. So we're going to come back to Eratosthenes, but it does burn. It burns on several occasions. Yeah. In 250 BC, it still exists. Yeah, it's burned once the Holy Roman Empire once the Roman Empire, so Constantine converts to Christianity, and well, once the emperor says we're Christian, we're all Christian now, it's time to be Christian, everybody, so that you get the Holy Roman Empire, and you get this giant library full of pagan books. What are you going to do with that? So it's crushed in the 300s by Christian mobs. Then in the 600s and 700s, there's an Arab invasion, and then it's completely destroyed. But what little of it is left is what the Arab scholars who come after the Arab invaders come and take that knowledge and bring it to Baghdad. And Baghdad becomes the cultural capital of the world for the next 800 years. So we're gonna get to all of that. I'm getting ahead of myself. But at this time, it has not yet been burned because there have not yet been Arab crusaders or Christian crusaders to destroy it. So that's Eratosthenes, but he's in Alexandria. Archimedes is not in Alexandria, but because he has this correspondence with Eratosthenes, despite the fact that he's in Syracuse, he has all the great knowledge that they have in Alexandria and then some. So among the most famous things, this is the only date I actually know, is 212 BC, which is when Syracuse falls to the Romans. So the Romans for years are trying to, right, you got the Greek Empire and the Roman Empire, and this is one of those points of friction. And the Romans are trying to invade, want to conquer. So in 212 is when they finally do conquer Sicily. But Archimedes is an absolute master of designing all kinds of, he understands leverage better than anyone else in the world. So levers, you know about levers, right? Levers. He understands the principle of leverage. So if I weigh something here and something here, so this is like, let's say 5 times the distance of this. This is like 1 meter and this is 5 meters. How much, let's say there's 10 pounds weighing here. How much should I put here so that the lever is balanced if this is the fulcrum? Why did you say that? Exactly. So the amount of force being applied at this distance is the multiple of the distance. So if I put 2 pounds here, that will pull just as hard as 10 pounds that's 1 foot away. Okay, so if you're, what's that? There's all kinds of rumors about what he actually did, but there are tales that he would build levers so long that he could lift the Roman boats out of the water. Just take an entire boat and, you know, with like 10 guys, they would just pull on this thing that had a huge long arm with a fulcrum all the way over here. And this is presumably nonsense. But he certainly made all kinds of weapons of war that were really, really inventive and had never been used before. And the Romans took a long, like, I don't know how many thousands of men they lost in the process of eventually taking Sicily. But they would have like imagine, you know, here's like the cliff, okay, and here's the river, and here's a Roman boat. And Archimedes is over here, and he sets up a giant fulcrum, and he sends a hook like this, and maybe this is 1 and this is like 20. I don't know, maybe there's a hill over here, and he gets 10 guys to hang on this. And because this is so long relative to that, it literally lifts this boat out of the air, and all the sailors fall into the water. It's like, this probably didn't happen, but there's so many stories about what he did to them. Amelia. That's him. That's him. Give me a yeah. That's a famous line of his. Give me a lever long. Archimedes. One of his famous lines is, "Give me a lever long enough, and I'll lift the world." Okay. So he understands there's no end to this principle. Also, the lever has to be strong enough, and also you need a fulcrum somewhere. But never mind. There's also the story of him needing to. There was like a crown. The king asked a jeweler to make a crown for him and gave him, a bunch of gold to form it into a crown. And then he was like not sure if the gold, if he just put a bunch of silver inside and just coated it with the gold and kept the gold for himself. So once it's done, how do you figure it out? You don't want to break the thing apart because now you've ruined it. So how do you figure out if it really is gold or not? So if you weigh it, it weighs the same amount as the weight of the gold that he was originally given. So Archimedes is thinking about this long and hard for an entire, day and a half. He can't figure it out. He gives up. Laura, you want to tell the rest of the story? How did he figure this out? He got into the bath. He's like trying to think about this problem, and he gets into the bath. And as he gets into the tub, he sees the water level rise. And he goes, "I got it." Except he yells, "Eureka." And he jumps out of his tub and starts running to the king, forgetting that he's completely naked. So this is like, you don't do the Olympics anymore, right? It was banned. Okay, I'm getting in trouble just for reminding you that used to exist. Anyway, it was the original nude Olympics. So let's just say realizes that to determine the density of a crown of what may be gold, not only do you have to check the weight, but you'll see how much water it displaces, and that will weigh it again underwater, and screams Eureka, running through town naked on his way to, he's figured it out. Like, I got it. Okay. One more story about this is that he would set up parabolic mirrors, just to tell you another story. So a parabola has this amazing property that it will focus wherever the focus is. The reason it's called a focus, like anyone who's wearing glasses, you're using the fact that a parabola, any light that comes in will be sent to the focus. So sunlight comes in at these parallel rays, and he would have apparently a whole array of parabolic mirrors, and they would focus the light right onto the ship and either burn the ship or burn the sailors that are on the ship. And so he was this incredible guy. Eventually, in 2012, which is the year of his death, as you'll see in a second, the Romans do conquer Sicily, and Marcellus, who's the general, is so amazed by this guy Archimedes. He's heard all these he's seen what he's done to his men. It says to a soldier, "Bring me this great man Archimedes. I have to meet him. I have to talk to him." And the soldier goes to talk to, to summon Archimedes. And Archimedes is, working. He's like working on a problem in the sand. He's drawing a bunch of very complicated circles. He's sitting there thinking about what's going on. The soldier comes over and says, "Come with me immediately. The general needs to see you." And he's stepping on his circles. And Archimedes goes, Hey, you're bothering my circles. What are you doing? Hang on. And what does the soldier do? He just kills him. He's, he doesn't know what he is. He's just some idiot. Doesn't know who he's talking to. Just walks up to him. Archimedes says, "Don't disturb my circles." The soldier says, "You don't talk to me like that. I'm a soldier." Just kills him. And there ends the great Archimedes. We're going to talk about what Archimedes did. These amazing contributions are not nearly as amazing as his actual contribution to science. Okay.